Okay, so here the goal is to find the maximum area of this rectangle that's inside of a semicircle whose radius is 28. So the area of a rectangle is base times height. I don't know the height, the base is x. A radius is 28. There are many radii that we can draw in this semicircle, but the one that best serves our purposes is this one here. That is the one that we want to play with. Right angle there, it's a rectangle. Now, if all of this is x, then this would of course be 1/2 of x. I don't know what this is, but I'm going to find it. We're going to find it for now. Let's just call it a temporary variable y. Let us go Pythagorean theorem. A, B, and C. Feed those values into the Pythagorean theorem. Okay, so here we have the value of y, which is in terms of x, which is a necessity because the area has to be only in terms of x. So we can jot this down. The area of this rectangle, the area of the rectangle is base, which is x, times the height, y, which is this value here, the square root of 784 minus a fourth of x squared. If the only goal is to find the objective function, then this is our answer and we are done. Okay? But let us assume that we actually want to find the maximum area itself. So let us proceed with this if desired. If all we wanted was this, then you're done. You can turn off the video. But I'm going to keep going and I'm going to find the actual maximum area of the rectangle. So as soon as I hear max or min, we need a derivative. So let's find a prime. So recall that here, this is a product. So we need the product rule. So it's the first one times the derivative of this. Well, the derivative of this would be 1/2 right? Because the square root means a power of 1/2. The 1/2 drops, you subtract 1, but also recall that there is a chain in here. Students will unfortunately forget this part. So we need the derivative of the of the radicand, as they call it. So the derivative of this would be what? Negative 1/2 x. So let us continue with the product rule. First times the derivative, second, all of that, plus the second times the derivative of this. Well, the derivative of that is just 1, so really it's just that term there. So we find the derivative a prime, and we always set it equal to 0, because that's where your tangent is horizontal. It would be the maximum at that location. So set this equal to 0. And why don't we multitask and save ourselves some time? If I put a 0 here, I can move this term to the other side and make it negative. And we can clean up this term while we are at it. So if you were to clean up this term, you'd have a negative x squared above. And that would be below. Why don't we now perform a cross product? Let us cross multiply here. Okay? So this times that is just negative x squared. This times this would be negative 4. And then the square roots undo one another. So we get back this here. The two negatives can become positive. We can distribute this while we're at it. I do have a calculator on me. So 784 times 4 is 3136. Minus x squared. Add this to this side. Half of 3136 is 1568. And square root. So all of this magic takes place when x is this specific number. So to find the actual maximum area, go back to the function that we created. But instead of x, you substitute in this number here and there. you can do that without me. I'll do it on the calculator in just a second. So again, x is this. Put that in here, in here. Let us put that in and let's see what we get back. So I got back 784 square units. So assuming that they actually wanted the area itself, it would be this number here. If all they wanted was the function, you'd give them this, but I'm pretty sure that they will require this from us as well. So that's how a problem like this can be performed.